a new topic. But like I said, the lab this week will be able to go over a little bit of Bootstrap one more time. Okay, so you will get the exercise. And like I said, I think once you start doing the project, I think it will also start to make sense to you as well, because that will be the case that you start to think about how you're able to do hypothesis testing. And then if only one sample is available, then you will have to do a bootstrap away because you don't have access to the population. Okay. Okay, so the new topic, topic 20, is center and spread. Okay, so this, many of you probably already know about like how to, what a mean is, what is the average, and what a standard deviation, what is variance. Okay, so maybe it's not new to many of you. And I just want to say that we add this topic here because for any kind of situation, or especially later, if we're trying to introduce the normal distribution that we also can be used to do hypothesis testing, then for any kind of distributions that we're introducing, we will be interested in certain characteristics of it, right? Like center is one thing because you want to know the typical value, okay? And spread, well, like how variable it is another thing that we care about. So we want to introduce this topic before we dive into even a little bit more about how to use the methods for hypothesis testing. Okay, so this is the reason why we do this. Okay, and all right, so just a few questions to all of you, and then I will put you in a breakout room so so I can take a break as well. So how can we quantify natural concepts like center and variability? Okay, center, okay, like the middle point, right? Variability is like the spread. Okay, why do many of the empirical distributions that we generate come out bell-shaped? Okay, so this is, if you remember, well, most recently we did this one, right? Sort of bell-shaped, okay? Sort of symmetric, okay? So this is another sort of question that we wanted you to think about. And then lastly is, how is sample size related to the accuracy of an estimate? Okay, so this is open-ended questions, but I do want you to take the time and meet with your breakout room members to think about those questions. So this is page 3, okay, page 3 of the topic 20 if you need it when you go to the breakout room. And now let me create the breakout rooms. Okay, yeah. So I should say probably the first question will be most straightforward to answer at this point, okay? Because the next two is what we're trying to answer for you as well, for not only for this topic, but a little bit later as well. Okay, so any thoughts about how can we quantify natural concepts like center and variability? Okay, any thing that come to your mind so far? Like we talked about a few, like say mean. Okay, I'm gonna say one thing, mean. Okay, as a center estimate. And Xia, do you want to share what you think about like other?
Yeah. Well, we were thinking, I mean, if you think about the range of the values you have and trying to find, you know, the midpoint of that, I guess it kind of depends on the question you have and what context there is, but yeah, I'd say the range is important.
Yeah, no, great. So range, if we all remember, range is like the maximum value minus the minimum value. Okay, so that I should say, yeah, definitely to some degree tells us about variability. Okay, and we're gonna review that coming up as well. So that would be a good candidate, okay, for variability. And earlier I just said mean will be a good candidate for center. Okay, anything else that you have heard or we have worked on? Everybody, I guess, not just Sha in the chat. Yeah. Anything else that comes to your mind when you think about center variability? We have been using one quantity a lot. If I try to recall, and that is the median, if you guys remember. Okay, median is the middle point. Okay, and that will be a good another good candidate, okay, for the center as well, because that's also telling us like a typical value, okay, right in the middle. Okay, and I would just say that, sorry about the, okay, yeah, sorry about that. And but I would just like echo what Xia was saying, because it really highly depends on the distribution or the data that you're working with. Okay, sometimes one measure is better than the other. Okay, like mean and median, we're gonna actually look at in what situations you want to use mean over the median, and in what situations you want to use median over the mean. Okay, that's one thing. And then also range, like I said, what Xia was saying is a good measure for variability, but there could also, but I guess I should put it this way. Each measure that we're gonna come like talk about has its pros and cons, okay? And the pros and cons are determined based on, like, I think exactly what Xia was saying, depends on what kind of distribution that you're working with. Okay, so we need to keep those in mind. And this, again, will be related to, well, if you're going to come up with your hypothesis, right, for your or research question for your final project, you might also start to think about, well, what will be a good statistic that I should be looking at, right? And then even if, like, say, if you remember, let me just bring that up one more time. This is the final project, right? And then the final project, like I said, you need to, for this, by the end of this week, you need to go up to part 3, right? Summary statistics and visualization. Okay, so summary statistics, like just say, if I want to know like a good estimate of the center of this distribution, right? Then you might want to think about, and then also write down your reasoning of, oh, in this case, I want to use the mean over the median because blah, 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 blah. Okay, so again, this topic 20 is where we're going to talk about in what situations one is better than the other ones. But just keep us in mind, I think, that this is pretty relevant. Okay, we're not just trying to talk about those concepts to you, but more about how we're actually being able to use it in practice. Okay. All right, so, and then also we're going to try to answer the question, okay, why do many of the empirical distributions that we generate come out bell-shaped? Okay, and it's not like a miracle. Actually, I wouldn't say, oh, how can I put it? It's not like a mystery, I should say. Oh yeah, go ahead.
I mean, for this one, I'm not entirely sure if this is correct, but when you take any sample of data, you're gonna get, I mean, you're gonna have your average value, and it makes sense that most of the values are gonna be around that. And then as you go out and farther away from the average, you're gonna have the outliers, but there are not gonna be as many of them. So it makes sense that it'd be bell-shaped, centered around your average.
That's a good point. And I guess I will also have some counterpoints to that in a second. But I wonder, like, say, anybody else, like, based on what Shell was saying, like, why empirical distribution that we generate come up to be bell-shaped? Any quick comments and feedback to what she was saying? Okay, yeah. All right, yeah. So I think it's a good idea to think about what is likely. And then of course, when we say it's bell-shaped, so let's come back to this bootstrap, okay? When we say bell-shaped, right, it's like more center around the mean, whatever the mean is, right? And then going slowly down, it's sort of symmetric, okay? So the only thing that I would just point out to what Xiao was saying is that I think, Xiao, you're referring to the histogram. Each of the data points that we're plotting in the histogram is a actual data point, like a data observation. Yeah. And what we are referring to, which you will become clearer, I hope, is that we are talking about the empirical distribution, not so much of the observations themselves, but of the test statistics. Okay. Like we're talking about, like, say, in this case, what it is, it's the bootstrap mean, right? In previous cases, I don't know, it's like the median or whatever that we can come up with. Okay. So a really important result that we're going to see in the next topic is that in the end, for many of the empirical distributions of the statistics that we're interested in, especially like a quantity like mean, you're usually going to come out as something like a normal distribution. Okay, again, we're going to, in the next topic, going to talk about what we mean by those terminology. Okay, but I just want to highlight that there are two things, right? Like the sample distributions are about the observations, like it's about the distribution of the samples, meaning that we're talking about the observations themselves, okay? And for that, just to like add to what you said, is that it could actually be any kind of shape, right? It doesn't need to be like, you know, bell-shaped per se, okay? Because you can have, like, say, all of the observations at one extreme, okay, and only one, like a few at the other. So that would not be something as bell-shaped as we hope, okay? But it doesn't matter in some sense that even if you have a super weird distribution of the observations, but if you're doing what we're doing, repeated sampling, right, of the test statistic out of multiple repetitions, then that test statistic, the empirical distribution of that, going to usually come out as a bell-shaped distribution. Okay, so, well, I guess I already sort of answered the question to some degree, but then only I think after we get to topic 21, it's going to become more clear, hopefully, about why things work in this way. Okay, and then of course, the last one is how is sample size related to the accuracy of an estimate. Okay, so I think we already had a good sense of when you take a sample, you want the sample to be large enough. Okay, otherwise you might not be really representative of the population. And then, of course, any kind of statistic that you computed based on the sample might not be a good estimate for the parameter of the population. Okay, but then of course we're gonna talk a little bit more about, like, say, because this question is a little bit more complex, right? It is related to the accuracy of the estimate. Okay, so we know that sample size needs to be large to make it more accurate, but then there is actually a mathematical relation. Let me just put it that way. There is a mathematical relationship between the sample size and the actual accuracy, and we try to quantify that. And then, so that can be a rule of thumb for us to determine how large is the sample size, right? Do we get a large enough sample size? And if this is too small, what else we can do? Okay. All right. So I hope, yeah, so we're going to start with this question. Some of them can be answered, some of them not yet. And to continue, let me just, yeah. So to continue our discussion here, let's start talking about the average, or like another way to call it is the mean. Okay. So this is one way we're going to measure the center. Okay. All right, so this is pretty arithmetic at this point, but we're gonna, again, I think it's important to talk through, and then we're gonna see how to do it in Python. Okay, so let's just say we have 4 data points. Okay, 2, 3, 3, 9. Okay, the average, if I do the math, is 4.25. Okay, and just a few features of what a mean or average is. It does not need to be a value in this collection. Okay, it is the arithmetic mean. Okay, so like in this case, the mean is 425. It's not any of the 4 values that we can see. Okay, but that's fine. Okay, and also it does not need to be an integer, even if the data are integers, like what we're seeing over here. Okay, it is the arithmetic average. It could have multiple decimal points, and it doesn't have to be an integer, even if the data are. It is going to be somewhere between the minimum and the maximum. Okay, but not necessarily halfway in between. Okay, and then the halfway in between stuff, this term we're talking about, is going to be more related to the median. Okay, so remember, the median is the middle point, right? And it's the 50th percentile. Okay, right in the middle. Okay. The fourth characteristic here is that the average or the mean going to have the same units as the data. Okay, so here there's no unit, it's just 2, 3, 3, 9. So okay, but like for example, the data set, like the maternal age data variable that we work with in the baby data set, the average is going to be age, right? So it's going to be in the same unit as age, which is the number of years. Okay. And also, we can think of the average as a smoothing operator. What we mean by that is that you can sort of collect all of the distributions in one big plot and then split evenly. That is sort of one way that you're able to think about how the average is being done. Like right now, it's only 4 values, so it's kind of straightforward. But what if you have a super large data set, and then what we're working on is almost like a smoothing operator that we're talking about here. Okay, so we did prepare a short demo. And this, again, could be useful in some cases, okay? But like mostly we're trying to introduce you those functions or methods that you can do mean calculation, okay? So for our values, remember we have 2, 3, 3, 9, okay? So we make an array, okay? And we make an array so we're able to work with it, okay? So the arithmetic mean, if you think about it mathematically, like what we do, we add all of them up, right? And then divide it by, so in this case, we add 2 and 3 and 3 and 9. And then we know that there are 4 values in this, right? So we divide it by the length of it. So mathematically, if you wanted to compute the average, what you do is you take the sum, right, of this array and then divide it by the length of the array, which will give us 4.25, like what we show in the slide. Okay, but then of course there are more efficient ways to do it. Okay, in Python, if we're using this NumPy, if you remember like the MP library that we'll be using, you can use mp.average. Okay, that will give you the average. Okay, you will the mp.mean will also give you the average or the mean. Okay, so whichever way you want is totally fine. Okay. And then of course, if I wanted just to like really double check that my work is fine, I can always add up those values. Like I don't need to work with the values array anymore, right? I'm just literally doing 2 plus 3 plus 3 plus 9 and then divided by 4. This is using Python as a calculator, okay? And then that gives me 4.25, not surprisingly, okay? And one last way I wanted to talk about how we think about the mean is what we mean by the weighted average. Okay, so like say here, because it's average, right? Mean is average, but More specifically, it's a weighted average because you also need to account for how many times a particular item occurs in this set. Okay, so for us, there are 4 values, right? And then 1/4 times it's 2, right? 1/4 times is 9, and 2/4 times is 3. Okay, so another way to do the calculation is to do 2 times 1/4 plus 3 times 2/4, okay, plus 9 times 1/4, which again brings us back to the mean calculated. Okay, so again, there are so many different ways to think about it. I just wanted to bring this up as well, because in some cases, it is also easier to think about this kind of weighted average when we're talking about the average, okay, especially when you're working with a small set like this, okay? Okay, so we can also, of course, now we have a array of all of the values. So how about we turn into a table so we can do some graphing? Okay, the graphing might not be that interesting or exciting, I would say. It's really just showing you the value in a histogram, okay? But we do see, so here is the percent per unit, okay? So don't forget the height, okay? It's not the frequency, okay? Only the area is the frequency, right? The height is the area divided by the width of the bin, okay? So we have, if you remember, 1, 2, right? And then 2 3s. Oops. That's why we have a taller one up here. And there's 1 9, okay? So this is how, if I try to graph it, okay, that will be, okay? Another thing I wanted to, I guess, ask you and think about is, what if I have 10 of 2s, 20 of 3s, and 10 9s? What do you think my mean gonna be? Let me repeat the question. Okay, so in the original set, we have what? 2, 3, 3, and 9. Okay, and then we calculated just now is 4.25. Okay, so now my question is, instead of 1 copies of 2, 2 copies of 3, and then 1 copy of 9, I'm having 10 copies of 2, 20 copies of 3, and 10 copies of 9. What do you think my mean gonna be? Is it going to be the same as 4.25 or smaller or larger? What do you think? Arithmetically, sort of. Like, you don't need to do it like out by hand or Python, just like intuitively, what do you think?
It should be the same, right? It's like the ratio of all the numbers are the same.
Exactly. Yeah. Thanks, Mike, and also Eli in the chat. Yeah. So indeed, especially if I come back to this, right? This is a weighted average, right? Like here we have 1/4, 2/4, and 1/4 for all of the percentages, right? And then if I just expand 4 into 40 and then each is repeated 10 times, then the percentages wouldn't change. So the arithmetic mean won't change either. Okay, so just so you know, if we do that, then you will see that it's also going to give us a 4.25 with regardless of what kind of method function you're using, and then the plot will just look pretty much exactly the same. Oh, it is, let me put it this way, it is actually exactly the same, okay? Because remember, the height is not frequency, okay? If it's frequency, then it's going to be slightly different, right? Because we have 10, 10, 20, 10, whereas it's 1, 2, and 1. But however here, anyway, so this is what we mean by the mean, okay? And then how we can compute it. Okay, so now let me ask you the question, okay? So this is page 6, okay? And you might want to take a look at it as well, because I will put you in a breakout room in a second. Let's just say, okay, the question says that create a data set has this histogram, but don't worry, this is given to you. And what are its median and mean, and why? Okay, I should say, maybe not why, and let me put it this way. What are its mean and median, and how do they compare to each other? Okay, so let me stop share here really quick and let me resume really quick, sorry. So there is one question, so since I'm putting you a breakout room, so let's go over. So the first part of this is asking you on page 6, okay, what are the mean and the median, okay? The second question now is I'm shifting, okay, some values further away, okay, from the cluster of the data. And then the question for you is that, are the medians of these two distributions the same or not? And what about the mean? When you say they're different, which one is bigger and which one is smaller? Okay, so take your time. You do need to, I think, go to topic 20, okay, page 6 and 7. So there are 3 questions, 3 graphs, 2 or 3 questions-ish together. and I will put you into your breakout room. And okay, so there are a few parts, okay? And the first part here, and I guess maybe just to type in the chat what you think, whether they're the same or, okay, I should say, what are its mean and median based on your guesses by reading the graph? And what do you think? You can type in the chat like mean equals to what, median equals to what? So we can maybe get a quick poll over here so we can get the discussion going. Okay, so this is, if we call it like a symmetric distribution, okay? Like say it's centered at, in this case, I think 3, right? And then looks like the frequencies, even though like the height, we know that it's not about frequency per se, right? But the area is, right? And then we know that that will give us roughly some ideas of how to guess what the mean and the median are. Okay, so what do you think? What do you think the mean is, and what do you think the median is in this case? Anyone? All right, thank you, Ayo. Yeah, don't worry about that question mark. Cross that, you're good. Okay, so mean and median, okay, both are 3. And the reason is, okay, so median is the middle point, okay? So I guess hopefully that makes sense to you because this is centered at the 3 value, and then it's directly exactly symmetric, so we know that median will be 3. Okay, and mean, actually, even though we're not like doing like the calculation arithmetic right now, like by looking at the graph, but since it's symmetric, right, like it's canceling out, right? If you imagine like mean is the middle point, right? And then whenever you have like a 2, you have another 4, right? Whenever you have a 1, you have another 5 in this case, because they're exactly symmetric. So the mean going to be 3 as well. So this is the case that it is symmetric, okay? So the mean and the median are the same, and then we can actually also tell from the graph that it's going to be 3, okay? So the second set, thanks to Ayo, and the second set here is that now I have my original graph here, okay? And a few values, so all of those 5 all of a sudden are moved to 10, okay? Everything else stays the same, okay? What is the mean, or roughly your guess, and what is the median here? And most likely they won't be the same, okay? So maybe the follow-up question is, if you think they're different, is mean greater or is median greater? Thoughts? Feel free to type in the chat or just speak up, because I cannot see everybody's faces. So if you raise your hand, I probably wouldn't be able to see. So don't worry, just speak up if you want to give any comments. Okay, so maybe the easier one is median still at 3. Okay, thanks. Okay, same median, larger mean, great. Mean is greater than in the right graph. Okay, awesome. Thanks. Yeah, Samantha and Sandy here. So I was about to say, if I compare this to, right, especially like just look at the right one, the median will still be 3 because it's centered, right? I mean, sorry, I shouldn't say centered. Even though it's not symmetric, right, it is still the middle point, right? And what I'm moving is only like the extreme values to make it even more extreme, pretty much, okay? But it doesn't change the ordering, right? Once I do a sort, right, and you think about how you're going to do the percentile function, right? You sort it from the smallest to the largest and then find the middle point, which will give you the median, but you wouldn't change for that matter for the right graph, okay? However, you will change the mean and actually going to make the mean larger, right? Because, well, earlier I was saying that when you have a 2, you get a 4 to cancel out, right? When you have a 1, you get a 5 to cancel out. Here, when you get a 2, you get a 4 to cancel out, sort of. But then all of your like counterpart of the ones, which used to be 5 and now are becoming 10. So not surprisingly, when you add them up and then still divided by the same number of records or data points, you will have a larger mean. Okay, so great intuition. It is exactly true that whenever you are having a not symmetric distribution, okay, let me put it this way. If you have a symmetric distribution, the median and the mean are the same, okay? When you have a non-symmetric distribution, then median will still be the middle point, right? But the mean will probably be a little bit more affected by more extreme values, okay? So that's another reason, like I said, at the beginning of this topic, I was saying that both of them are good measures, right, for the center. But depending on the distribution of the data that you're working with, sometimes you might prefer one over the other, okay? So in here, we have a summary slide, okay? So mean, okay, is the balance point of the histogram, okay? Median is halfway through, okay? Halfway point of the histogram or the data. So if the distribution is symmetric, then mean and median are the same. So you can use whichever sort of, right, to describe the center. If the histogram is skewed, meaning that it's not symmetric, okay, then the mean is put away from the median in the direction of the tail. So if we come back to this example really quick one more time, okay, here. So this is the case that is skewed, okay, it's not symmetric, okay? And we're saying that the mean, so look at the language here, the mean is put away from the median in the direction of the tail, okay? So the mean used to be 3, right? And median is still 3 here. The mean is put away from 3, which is the median, okay, in the direction of the tail, okay? The tail meaning that, well, in this case, just like what is longer, right? Like the tail to the right. So just like what Samantha and Sandy were sharing in the chat, the mean going to be larger, and this is, and it's understandable, just like the statement over here, because it's going to be put away from the median to the direction of the tail, okay? So if we think about this, then if you are working with a variable, right, that is skewed, then mean might be a little bit too easily affected, right, by the extreme values, okay? And that might be a reason why you might want to report the median instead of the mean when you're working with a symmetric distribution, okay? So like I said, if we come back to this example, what I mean by that is that, well, just like what we're thinking about how we can compute the mean, right? Even though we don't know like the exact values and how many there are. But what I was saying is that, well, the mean going to be, because it used to, all of those values of 10 used to be 5, right? And then it's balanced out, okay? But now those 5s becomes 10, right? And they are in some cases like sort of a more extreme than the cloud of the data, right? The cloud is from like 1 to 4-ish, right? It used to be 1 to 5, but now all of the 5 become 10. So I was saying that those are more extreme values to some degree, right? And then this value is going to have a big impact on the mean, but it wouldn't affect the median, at least in this particular example, okay? And because of that, we are actually going to use the median, I think, more in the case where the histogram is skewed, okay? Because the mean might be easily affected, in this case, indeed, easily affected by those extreme values, okay? And so keep that in mind, okay? And I will also just put one more discussion question. In this case, which one is larger, the mean or the median? This is the height, okay, of in inches of all NBA players in 2013. Which one is larger? So I guess we consider, well, it is a skewed distribution, right? And we know that if it is skewed, then the mean, so let's come back to that slide, the mean going to be put away from the median in the direction of the tail, okay? So the tail is to the left, okay? Yeah, so this, I guess, the median going to be larger, okay, because the mean going to be put away further to the left, slightly, okay? Actually, they're pretty similar. So in fact, we do have, I think, oh yeah, this one, we do have a quick, yeah, the data it's available, okay? So if we only get, so that's how we got the histogram in the first place, okay? And then the median, okay, use the percentile function, okay, is 80. And then it's very close. The mean is 79, okay? So, but like I said, mathematically, like numerically, we're able to verify that, but also just like intuitively, hopefully it starts to make sense to you that if you're working with a non-symmetric distribution, like a skew distribution, then the tail of the direction is gonna be how the tail is put away from the median too, okay? And sorry, how the direction, I guess, of the mean put away from the median. So in this case, it's going to be further to the left a little bit. No big difference, I guess. 79 and 80, but it's a non-symmetric distribution. So we see that feature happening. Okay. Oops, sorry. Okay, so that's about the mean. And let me talk about the standard deviation, which is a way to measure the spread. Okay, but we're gonna first start with thinking about what Xiao was saying. Okay, defining variability. The plan A is what Xiao was suggesting. Okay, we can look at the range. Okay, it's the largest value minus the smaller value, or the maximum minus the minimum. Okay, One drawback here is that it doesn't tell us much about the shape of the distribution, okay? In a sense that, well, imagine I have a bell-shaped distribution, let's just say center at 3, right, earlier, right? And the lower goes to 1, the larger goes to 5, and it's symmetric, okay? So the range there is what? 5 minus 1, which is 4, okay? And let's just suppose now I have a different distribution, which have half of the points at 1, okay? Half of the points at 5, okay? The same number of points out there. So the range will still be 4, okay? But the shape is so much different, right? From the symmetric that I was talking about. So that's the drawback, I think, of using a range directly, okay? Because it does not tell much about, even though it does tell us like the spread to some degree, right? Like the largest minus the smaller, like the range of the data, but it doesn't tell much about the shape, okay? So another one, which is much more commonly used, is to measure the variability around the mean, okay? So like this measure requires you to know the mean first, okay? Like say, if I get a set of data, right? I compute the mean and measure the variability around the mean and then try to produce it as a statistic, okay? So the way to quantify this, okay? Let me show you in the demo and then I think we will be done for the day, okay? All right, okay. Okay, so we come back to this toy example of 2339, okay? So, all right. The standard, okay, so this is the table 2339, okay? The average, okay, we computed before is 4.25. We save it in object because we want to define, like you will see how we're going to define what we mean by variability around the mean, okay? So we're actually calculating deviations, okay? Let me show you what we mean by that. So we have a column of the value, right? And then we compute the average, okay? And then what we're doing is that we're computing what we mean by deviations by using each of the value, subtract the average value that we just computed, okay? And then we attach this array as in a new column into the original table, which give us this. Value is still 2339, right? The deviation defined to be the value minus the mean is negative 2.25, negative 1.25, negative 1.25, and then 4.75, okay? So deviation, okay, is one way we defining it is just looking at the value minus the average, okay? One thing about directly using the deviation is that if you just sum them up, they become 0, okay? And it's not surprising, right? Because the mean is computed as the sum divided by like the number of records in here, okay? And the deviation, well, if you like multiply this by 4, right? And then the value just sum up, well, the difference is going to be 0 by definition of the average in the first place. Okay, so I bring this up because yes, the deviation is useful, okay, but directly like summing them up or using it might not be as useful because the sum is 0 by definition because of the way that we define the deviation. Okay, so what typically is done, okay, is we actually going to square the deviation. Okay, so deviation can be negative, positive, right? And then that's why when you add it up, it's going to be 0 because of the design. But instead of like summing them up, what if we take the square of the deviation, okay, which is what I'm doing, and adding it into a new column? Okay, it's called the squared deviation. So it's 5 point something, 1.5, 1.5, 20, 22.5-ish, okay? And then what we do is instead of, okay, summing the deviation itself, what we're doing is that we square the deviation, sum them up, and then take the mean. Okay, so that's what we mean by the variance of the data. Okay, so to like do all of this in like, you can always write it up, like say that one function will be able to get it directly, but I just want to like talk through it one more time. We have a set of values, right? We first of all get the mean. From it, we're able to get the deviations, okay? And then we take the square of the deviations, and then we take the average of all of the squares to determine what we mean by the variance. Okay, so the squaring step is useful. So we are getting rid of the negative or positive sign, right? Because it could be negative, could be positive, but what we really want to measure is for each observation, how far it is from the mean. Okay, so taking the square can help us to make sure that all the distance, right? All of this are distances. So distances should be non-negative, okay? And then we take the average to get a good sense of on average, right? How big the squared deviation is for each of the record. All righty. And then when you get the variance, if you take the square root of that, you get what we mean by the standard deviation. Okay, and then you can use the np.std, stands for standard deviation, STD. That will give you the standard deviation directly. Okay, so this is a typical measure. Okay, and I think, yeah, so on Thursday, we're gonna come back and talk a little bit about how we are, like how we understand the standard deviation and some other properties around it. Okay, so I'm gonna stop share, and yeah, feel free to stay over if you have further questions, but if you need to go, feel free. I think, yeah, we're a little bit almost running out of time now. Okay.
Computer. All right. Hey, happy Thursday, everyone. I hope everyone is doing well. I want to jump right in kind of just with a kind of a quick review. So last time we talked about mean and this idea of the mean, which is the average, which is the sum divided by the number of elements in our list. And then we talked about this notion of variability in the data. And what do we mean? And we tried to kind of quantify what do we mean by that. And variability in the data is how far are we from the average? How far are we from the mean from there? And we looked at a couple of notions of how we wanted to find that, right? And we came up with this idea of just measuring variability around the mean. And then we looked at a demo, how to quantify that. And if we look, so we take our array and we have just a simple array here with a couple of numbers in there. And the average is straightforward. It is the sum divided by the number of elements in the list. And then we kind of started playing around with this idea of how much does our data vary from the average? And so one thing that we can take a look at is this deviation. So if we have the average value and we subtract that from the value, that will give us, for each data point, how far are we away from the average? And if we take a look at that, we can see that we're values that are smaller than the average. So values that are smaller than the average will show up as negative, right? So in this example here, our average is 4.25, and this value 2 is negative, and so it is negative 2.25 units away from the average, right? If you take the value. And then the one thing that we noticed about this idea of looking at the deviations, right, because we're showing how far we are from average, if we take the sum of the deviations, no matter what distribution, no matter what data we have, the sum of all of the derivations are going to be 0, right? Because all of these or the difference from the average, they're going to have to sum up to be there. So that's probably not the metric that we want to have to kind of measure variability. And we kind of saw this again. We saw this when we looked at categorical, comparing categorical values. And we kind of came up with this distance metric, right? Where we're going to take, one thing that we can do is take a distance. We can take an absolute value to get rid of the negatives. But another thing we can do is we can actually take the square of the deviation. And we're going to see later, that's going to have some very valuable properties. And so if we take the square from that, notice all of our negative values, they become positive. And notice as we get further away from the average, the deviation goes up, right? Because we're squaring it. So the farther we go, kind of the stronger the weight is. And so now that we have this kind of this square deviation, so now the sum, kind of makes sense. And we can actually take the average of the variance, the average of all of these deviations, and that's going to give us this variance, okay? And so now that's actually now a useful metric, right? Because it's not going to be 0 all the time. It is actually going to give us some indication of how spread out this data is. But remember, because we did the square here, if we think about it in terms of units, for example, if we were measuring heights or ages, this variance, because we squared it, is not in the same units as our original measure. So the final kind of piece of this is that we're going to take the square root of the variance, and that is going to give us back to our original units, okay? And so this whole thing is known as the standard deviation. And formally, it's the square root of the variance from there. Okay, so we take the variance, take the square root, we get this number for our data set. And this is something that we do so often. NumPy has this feature built in, right? So we don't have to go through all of these steps. We can just take our array of data and we can just run it through the NumPy standard deviation function, and we get the same value. So that is basically what we would hope for that, and that shows this is exactly the calculation that the standard deviation function is doing. Any questions? Any questions about that before we move on? All right, fantastic, great. All right. All right, so why are we using the standard deviation? The big one is this Chebyshev's inequality, okay? And we'll talk a little bit we're gonna talk about that next. And what that says, what Chebyshev's inequality says, no matter what the shape of the distribution, okay, and this is important. So no matter what distribution of data that we get, the bulk of the data is going to be, and we'll get more precise about this in a second. The bulk of the data is going to live within the mean plus or minus a few standard deviations of the data. Okay, and so, and what's nice about this is that we don't have to know anything about, we don't have to know the shape of the distribution. This will apply to any data. And really why this kind of works is because the standard deviation captures this variability in the data. And so we can basically have this lower bound on, regardless of the data, about where the bulk of the data is going to lie. And the second reason we'll talk about, if we have time to get to it today, is the applicability to this normal curve, this normal distribution, and the central limit theorem, which we'll talk about. So there's a couple of good reasons why we use, in particular, this standard deviation as this measure of variance. And so a lot of times when we have data, one of the natural questions that we're going to ask is, where are most of the values? Where do most of the values lie in our data? And so Chebyshev's inequality gives us a bound on that. Regardless of the data, we can capture this notion of the data is going to be contained within a small number of standard deviations of the data. And in particular, Chebyshev's inequality basically says, if we kind of look down here, that the data that we're going to have, so if we look at this formula, at least one, right? So one would be the entire, all of our data, because we're talking about this as a percentage, minus 1 over z squared, okay? So, and z squared is this standard deviation. So the average plus or minus this z, and we'll talk about what z is, times the standard deviation. Okay, and so that's going to say our data is going to, that percentage of data is going to fall within that. I think it's easier to see when we actually put some numbers to what z is. So z kind of measured in standard deviation, standard units from there. And if we kind of see this for a couple of common standard deviations, we're going to say, if we take a look at our data, right? So we're going to look at standard deviations from the mean. So plus or minus 2%, 2 standard deviations gives us, plugging into that formula, 1 over 2 squared gives us 4, which is going to give us 25%. 1 minus 25% is going to give us 75% of the data. Okay, so if we look at, regardless of the distribution of the data, of any data, we know that 75% of the data is going to be plus 2 standard deviations, from the center, to minus 2 standard deviations from the center. And that goes up. And so, you know, kind of looking down at the bottom, plus or minus 5 standard deviations, this gets us 96% of the data, right? And that's over our magic number of kind of 95% from there. So we know, regardless of the distribution, within 5 standard deviations, either way of the mean, we're going to capture a bulk of the data from there. And the power, like I said, the power is that we don't need to know anything about the underlying distribution from there. The data itself might actually, so if we look at plus or minus 2 standard deviations, if we actually look at the data, more of the population, it might be more than 75%, given the actual data, given the actual distribution, but it will never be less. We will always capture at least 75% of the data, plus or minus 2 standard deviations for any distribution, but it could be more. That's what I mean when I say this is a lower bound from that. Okay, and so when we deal with these, these data, it's very helpful, instead of thinking about, you know, like heights or ages, because of this because of Chebyshev's bounds, right, where we can kind of quantify in these in standard deviations. A lot of times when we look at data, we don't want to we want to put it in a form where we're looking at the standard distribution, standard deviation, and so this gives a rise to this idea of standard units. And so the standard unit, this will tell us how many standard deviations are we above our average. And so to calculate that, we basically take our data, and so we'll have the average of our data, and we're just going to take the value minus the average, and we're just going to divide it by the total standard deviation. Okay, and so the way I kind of look at it is it's just normalizing the data across the standard deviation. And so same thing holds true when we were talking about the variation, right? A negative z means that value is below average. Positive z means it's going to be above average. And if z equals 0, it's going to be equal to our median, our average, our mean, not median, mean from there. Okay, and so when we take our data, if we do this conversion, and it's just this conversion, the value minus the average divided by this standard deviation, when we do that, when we look at our distribution, the average now, instead of being the mean, the average now is going to be 0, and the standard distribution of this converted data is going to be 1. Okay. And so when we move to standard units, and I'll show you a demo of this in a second, but when we move to standard units, we know, just looking at it, 96% of the data is going to be between these z values between -5 and +5, right? Because these numbers represent how far we are in standard deviations away from the mean. And in this case, when it's in standard units, the mean is now going to be 0. All right. I think it is high time for a demo. While I'm setting the demo up, please let me know if you have any questions. All right. So for this, we'll look at our birth table again, and again. So because we're going to convert our data, it's just very useful to have a helper function. And you can see that the helper function is doing exactly what we said we were going to do in the slides. And so kind of looking at this function in terms of inputs and outputs. So what's going to get passed in is going to get an array is going to get passed in. So this is going to be our array of our data in whatever units it was, feet, inches, years, time, whatever. And so then we're going to convert that array to standard units, and we'll return the converted array. And so what we're doing is we're passing in an array. And so here we're just using NumPy to take the average of the array. and we're subtracting. And remember, when we do subtraction, it's gonna do element-wise subtraction. So it's gonna perform this operation, we'll calculate the mean, and we're gonna subtract that from every element in the array, and we're gonna return a new array. Okay, so this whole thing, this part here is gonna be array, which is just the variance from the mean. From there, okay? And then finally, we're gonna divide by the standard deviation of the data. That's our kind of normalization from there. And again, the same thing applies when we do this division. We're dividing by a number here. And so it's gonna apply that to every element of our new array. So this is gonna return the normalized or the standardized array. Okay, now that we have that function, let's take the maternal age from our data set. And all we need to do to convert it to standard units is just run that standard units helper function on our data. Okay, and so now if we actually take a look at that, if we take a look in the conversion to standard units, remember what we said from our slides. Once we've done that conversion, our distribution now, the average is going to be 0 and the standard deviation is going to be 1, because we've taken the difference from the mean and we've divided it by the standard deviation, right? So the first thing that we did, that made us have the average in 0. We're subtracting from the mean for each of the data points. And by dividing by the standard deviation, now we've made the standard deviation 1. Okay, so these properties here fall directly from how we calculated that. And so no surprise here. If we printed out the mean, notice even though we get a number, look at what this is. This is negative 7.8 times 10 to the minus 17, right? So this number here with 16 zeros in front of it before the decimal point, right? That is virtually 0. And the standard deviation from there is 1, okay? So all of that math checks out. That works exactly as we would expect it to. And so now we can kind of add that back to our table. And so here's the age in years, and then this is the age in standard units. So how far is that age in the standard units? In standard deviation away from that. Okay, so if we print that out now, you can see that in our non-standardized units, we have the average. We have the average of 27, and the standard distribution is 5.8. Okay, so if we take a look at the histogram, so this is just our original data, we can see that bears out. And so one of the things that's kind of cool, and I think it's a good thing to always keep in the back of your mind is, so what is when we're looking at the mean of a histogram, what does that mean actually? And so the way I like to the book mentions this, and it's actually very useful, right? So if we go down, right, so 27 is probably like right around where my cursor is here. And I like to, the book really makes a mention that the mean is the balance point of this histogram, right? If we cut this out of cardboard or had like a 3D model of the histogram, if we put our finger right in the mean, or a pin or something there, or a fulcrum, right at the mean, this histogram would be perfectly balanced, which means the mass on the left side is equal to the mass on the right side. And so, and we see that, and that kind of makes sense, is that because we kind of have a little bit more over here, the mean isn't completely centered on our unit there, but right at 27.2, if we put our finger there, the histogram is going to be perfectly balanced. And then the standard deviation, right, is in this unit is in years. So one standard deviation is 27 plus 5.8, and 27 minus 5.8, one standard deviation from there. But now converting it into standard units, we can see that the overall shape of the histogram is the same. But now what happened? Now what happened is now it is very easy to see where the center of our histogram is. It's right at 0, right? So we put our finger right at 0, that's going to be balanced from there. And so now you can see that we've been normalized into standard distribution, standard deviation, right? So this is 1 standard deviation out, 2 standard deviations out, 3 standard deviations out, okay? From there. And you can see, do you remember, if we go back to Chebyshev's inequality, we know that 96% of the data is going to be contained within 5 standard deviations. But we know that that's a lower bound. The actual data can be contained in less than that. And if you can see from here, where does all of our data lie, right? So this is kind of all of the data. You can see that it goes out to a little more than 3 point maybe 1 or so, down to -2. And so we're well within that plus or minus 5 standard deviations range from there. Okay. Any questions about standard deviation, standard units, variability, anything that we talked about so far?